Now, last time we were talking about the conservation mass equation. This time we're going to be focusing in more on a very key detail, which is simply how in the world do I calculate my mass flow? That's the whole m dot thing. Where does it come from? Well, let's figure it out this time. So first off, we have this nice fancy equation right here, okay? This is the simple form. We have a mass flow in, a mass flow out, and we have a change in mass of my control volume. Or at least, sorry, that mass of my control volume is changing with time. I love that equation. It's super simple, and if you can simplify it to that, it's all fine and dandy. Now, typically, we're not working with bricks. We're working with fluids. And if we're working with fluids, well, we can put this mass of my control volume in terms of the density and the volume. Or I can do an integral because my density doesn't have to be constant. For every single problem in this class, almost every single problem, there's probably one in there, our density is going to be a constant. So you'll probably just see this form. But technically, it doesn't have to be constant. Density can change with position of your volume. So you could have an integral form too. Okay, now if that changes with time, then what I'm trying to figure out here is, well, my mass, my control volume changing with time is going to be equal to how this integral changes with time, or how this quantity changes with time. Now, mass is going to move in or possibly out from somewhere. It's got to, otherwise you don't have a problem because nothing's changing. And the best way to think about this is it's simply passing through a door. So if you want a lot of mass to go out, you either need a big door or fast people to move a lot quickly. You have to have one of those two things, or both, to be able to get out of here. So we're going to be developing a more complete and more complex equation right here. But just remember, all it is it's the size of a door and how fast stuff is moving through that door. So here we go. My mass flow rate net is going to be equal to this integral. Now this right here is simply saying I have a control surface, which could be something like this. It could be completely arbitrary. It is almost never arbitrary. Okay, I'm never going to give you random blobs. Typically it looks something like this. I've got a control volume. I have maybe 2 inlets. I have 1 outlet. And this control surface, it goes from an integral to being a sum. Okay, that's going to happen most of the time. So don't get freaked out by the integral. There's very few times where you have to worry about it in its integral form. Okay. Now the dA right here is simply the size of the door. So any of this, normally this is going to be a sum, everybody. The bigger the door is, the higher my mass flow rate. Now V dot N is simply the speed of the people, quote unquote, because we're dealing with fluids here. I'm just trying to, you're in a classroom, you're trying to think about classes. How do you get a lot of people out of place? Fast people or a big door? Or both. It really helps if they're both. Now, why do I have this dot N? Technically, that's the normal component, okay? That's the normal component of my velocity, and by having that, let's see, I think it's right there, yeah. By having that, I'm saying I only care about the component of the velocity that's normal to the door. Like, for example, here's my doorway, okay? And if people are walking through it, I want them to walk straight through the door. That makes sense. If they're walking like this, at an angle through the door, it takes them a long time to go through it. Now let's look at this from above just so you can kind of see what I mean. This is the fastest way to go through a door. This is not the fastest way to go through a door. Doesn't make any sense. So we only care about the normal component of velocity because that's the component that's actually pushing people through the door. Okay. Now we can also do this as changing with time. So this right here is simply saying our conservation mass equation that has now been brought into a more complete form. What it's telling me is that my mass in my system right here is going to be equal to the amount of mass, how my mass is changing in my system. It's going to be equal to the difference in the mass flowing in versus flowing out that I get from here. Now, integrals are scary. Who wants to deal with integrals? I don't want to deal with integrals. We don't usually use this equation. If you go into Arrow, you will see it more because we use it, but even then we simplify it a lot. And so what we typically do is something like this. What we do is we say, okay, yes, the amount of mass I have in my control volume is going to be equal to the difference between the mass flowing in and the mass flowing out. I completely did it in the wrong order, but the mass flowing out versus the mass flowing in. Remember, that's a sum. So I'm just looking at all the possible doorways and saying, okay, using these doorways, what's the difference in the mass flowing in versus flowing out? And that mass has to be stored in my system. So, thank you all for listening, and I'll see you all next time. Bye-bye.